Hello students, welcome to Optics 1 Concave and Convex Mirrors. So in this lab, you'll be working with a concave and a convex mirror. So a convex mirror actually reflects and scatters the light out, and a concave mirror actually converges the light together if the light comes from infinity. And by our definition here, the radius of the concave and convexity is twice the focal length. So in both cases, you would end up using the mirror equation, 1 over u plus 1 over v equals 1 over f, which ends up being 2 divided by r, because r is twice f. So when the light comes in, if it comes in a parallel, the convex mirror would actually scatter light out, but if you backtrace the imaginary ray, it would actually end up focusing at a focal point behind the mirror. On the other hand, when the light comes in from infinity, and then it would converge on the focal point in the case of a concave mirror. So image formation in a concave mirror, you can actually draw the line according to your coursework that when the light ray actually cross one another, you can actually call the crossing point the image formation point, and then you would call this object length plus u and this image length plus v for the concave mirror. However, if you push the object a little too far from the focal point, then it would be too far to actually focus the light to form an actual image. So in that case, the concave mirror would actually scatter the light out, and the backtracing of these lines would actually end up creating an imaginary image. So in the first case, the real image is formed in front of the mirror, and you can put a screen on top of it to measure it. And in that case, you use the v value to be positive. However, if the image is formed behind the mirror, you use the v value as a negative number, and that counts as the imaginary image. You can't put like a screen and get the image out of it. On the other hand, for the convex mirror, you would always get an imaginary image, because when you put a real object in front of it, the light would always scatter out. So you have to trace back the light ray to find the position of the image. So in this case, u, since it's in front of a mirror, u is always positive and v is almost always negative. And the mirror would actually have a negative value for focal length, because this is not a real focal point, it's imaginary focal point as well. So the formulation for the calculation of curved mirrors and lenses, they use the exact same equation, 1 over u plus 1 over v equals 1 over f, and the magnification is the division between the image height versus the image actual height, versus the object actual height, or you can conversely calculate it from minus v divided by u. Whereas for curved mirror, you would actually use f to be positive for concave and f to be negative for convex. So if the image is formed in front of a mirror, you use positive v, and if the object is in front of a mirror, you use positive value of u. Okay? So as for lens, things are reversed, so don't worry about it. We'll cover that on Optic 2. So in this lab, you're going to be using the parallax method, which is actually the cue that gives you the perspective of things. For example, if you look at this car, how can you tell that the front mountain, the road is in front of a mountain, and the mountain is in front of that cloud, and the sky back there is way behind? So the way you can see is things, when they are moving faster, you perceive them as being closer. This is parallax. Okay? So when the object actually fly like slowlier, that means your brain would perceive it to be further away. So this is the parallax method of creating object and animations. So the non-parallax method, to demonstrate that, please look at this model. So you can see that the two rabbits here, they're actually sitting on top of one another. So if you change the perspective of the way you view things, you can see that these two objects are actually sitting right on top of one another. So this is a non-parallax method. So no matter how you shake your head around, you will still see that object as being there without it moving. However, if you see the parallax, then occasionally you would have like the object that is actually sitting right on top of another one, but it's only apparently on top of another one from a certain angle. If you move your perspective a little bit, like shaking your head, you can see that the rabbit on the behind is actually like way back compared to the rabbit in the front. So yeah, by looking at things from one angle, it's not going to give you enough information to see whether or not if the object is parallax or non-parallax. So in this lab, you're going to be looking at the mirror and then shake your head around in front of the object and then see if you can form a parallax or non-parallax case. Okay, so yeah, as I mentioned earlier, when you use the non-parallax method, if the things are actually completely aligned with one another, no matter how you shake your head, you will see the object like completely aligned. But if it's not, then it would always, move against one another when you change the angle of vision. So you'll be using the non-parallax method to determine the object and the image that is formed. Okay. So in this lab, you're gonna have like this setup. So you're gonna have like the orange object as the object, and then you'll be using the yellow object as the image tracking device, and from there you can actually use it to calculate the distance of the object and the distance of the image from the mirror. So here, when you form a non-parallax image, so you can see that the image inside there and the actual object that is sitting there are actually lined up no matter how you change the angle. So if you change the angle, then you can see that it's sort of move with one another. So, but in this case, you can see that the object is actually moving faster than the image. That means the object is closer to us than the image itself. So this suggests that you move it a little bit closer into the mirror to actually form the non-parallax. So in case of non-parallax, you can see if you move your head completely left and right, these object on the top and an object on the bottom would always go together with one another. So this is how you form like a non-parallax image using the equipment that you have in the lab. So also, since you'll be using the yellow object to track the location of the image, so at some point you're going to be using the bent the 90-degree bent up image finder as the object. So when you use the orange thing as an object and the yellow thing as the image finder, what you can read is the center position of the object and the center position of the image holder. However, since the image holder is bent, so you need to measure what is this distance. So this distance you read is 31, so that is P. So what you want to know is what is the I, so the location of this bent part. So you need to do a little calculation at the beginning of the lab. So for example, if you will be giving this T rod, which is exactly 15 centimeters long. So if you put the 15 centimeters long rod between the object and the image finder, then you could actually tell that this distance is 15 centimeters. However, since you don't know that this distance is what, you have to calculate it. For example, in this case, since this is 10 plus 15, this should be around 25, right? But since you're reading P to be 31, then this distance is supposed to be 6. So this is the PI distance. PI distance in this case is 6. So if you look at this one, so you have to do this twice. One with the bent part pointing towards the object. The other one is bent part pointing away from the object to find the average PI point. So from here, if you bent it the other way, then the distance between the two rods will still be 15 because you're using the same T rod. However, since you move the P point closer, this time it's 19. However, since you know that this is 15 and this is 9, so you can tell that this part is 6. So on average, this would be 6.0 theoretically. But if you do it in the lab, you're going to have to actually conduct this and then measure it and average it to the significant figures. So first part, concave mirror. So you're going to be starting working with the concave mirror. So first of all, you want to put the object right where you can form the non-parallax method. So from there, you can tell that the distance between the object and the mirror and the image should be the same on the first case. So u equals v equals r. So whatever distance that you measure between the mirror point to the center of the object point is going to be r. So use that to estimate r, and then from r, you can calculate f by dividing it by 2. On the second part, you're going to move the object a little bit closer to the mirror and then use the screen to find the image location. Use this formula to find the f. So 1 divided by u plus 1 divided by v equals 1 over f. So just remember, move the object just a little closer, not too far, not past the focal point. Otherwise, you can't form the image. Okay? So concave mirror, you're going to conduct 2 experiments. Then, for convex mirror, you have 2 more experiments. Since you can't form the image using the convex mirror, you can be using the convex lens. So in this part, you will be placing the non-parallax method of the image that you can see through a lens by putting an object in front of a lens and a convex mirror. So the convex lens would actually focus the image formed from the object to be behind the mirror, so giving this the imaginary object. So this would give you the parallax method approachable. So you need to do the calculation twice, one for the lens and one for the mirror. And then second part, using the plane mirror, you use the plane mirror to estimate the location of the image formed by the convex mirror. So by using the plane mirror, you know that the distance of the object and the image is the same. So since you can locate this distance, then you can calculate how far the image is formed. And then once you get the parallax method working, non-parallax method working with this image formed by M2 and the image formed by M1, you can actually calculate minus v from this case. So the image formed here, through the calculation, you can actually get the image distance. Just keep in mind that the focal length of the convex lens is going to be always negative, and then if the image form is formed behind the mirror, then the object distance is going to be negative. So please be sure to write the value of v to be negative in this case to do your calculation, and keep in mind that the focal length and the radii of the convex mirror is always negative as well. Okay? All right, that's it. Enjoy the lab. Thank you.